We're continuing the analysis of the LP-STC, the low-pass single-time constant circuit, also known as first-order filter. So this is the magnitude body plot. And previously we discussed this, and we said that this is a plot of the dB level of the magnitude of the transfer function. And that's on the y-axis, 20 log magnitude of t. T is the transfer function, and it's a t of j omega in the j omega domain. The units are in dB, so this is a log scale on the y-axis. The low frequency gain is k. So at frequencies that are low, we get 20 log k. And then as we approach omega 0, things start to change. Omega 0 is this important critical frequency that has several names. One of them is 3 dB frequency. As we approach omega 0, the gain will start to drop. And then after omega 0, if the frequency is greater or much greater than omega 0, the gain will drop, and it will drop at a rate of minus 20 dB per decade, or a decrease by a factor of 10 when the frequency increases by a factor of 10. And this is as a function of omega on the x-axis, and omega is also log scale. So we go by decade. The step on the y-axis is a multiplication by 10. So we see the step is 0.1 to 1, and then 1 to 10, and so on and so forth. So the blue curve is the one that we get. This is the exact function, the exact t, or 20 log t, versus omega log scale. But there are also approximations to this, and these are the levels for very small omega. We get this level. And this is like an asymptote for the blue curve. And the other asymptote is for very large omega. And this is another straight line, but this has a non-zero slope, a negative slope of minus 20 dB per decade. And the two lines will intercept here exactly at omega 0. So this intersection point is exactly at omega 0. Now, these asymptotes can also give me a way to approximate the body plot instead of drawing or constructing the blue curve. I can easily construct the asymptotes because I know that one of them is the horizontal one, and it's at a level which is equal to the low frequency gain. So at the low frequency gain, which is this value here, 20 log k, I can easily draw a horizontal level, and that's the first asymptote. The second one, to build the second one, I know that for an LP-STC, it will be a slope of minus 20 dB per decade. So I know the slope. So I need I need a point. And the point is omega 0, this point here. So at omega 0, I construct the second asymptote. So it's a straight line that will have to go through this point, which is omega 0, 20 log k. And it has a slope of minus 20 dB per decade, or minus 6 dB per octave. So that's a very quick and easy way to construct an approximate body plot for magnitude, consisting of these two straight lines, the 20 log k level up to omega 0, and then after omega 0, a straight line with a negative slope of minus 20 dB per decade, and it will drop forever until very large values of omega. All right, so this is the magnitude body plot. Remember that t is T is not just magnitude. T of j omega is a complex number. So we start with, for this example, we started with a circuit that had a capacitor. The capacitor introduced S in the transfer function. So now it's a T of S. And when we go to the j omega domain, we replace S by j omega, and T becomes a complex number. Now, the complex numbers have a magnitude and they have a phase angle. The T of j omega is, well, let's start with T of S first. T of S for this example and for any LP-SDC for that matter is K over 1 plus S over omega 0. And if we go to the j omega domain, then we get T of j omega, and I replace S by j omega here, j omega over omega 0. So this is a complex number. It has a magnitude and it has a phase angle. And the magnitude is what we are showing here in this plot. This is 20 log the magnitude. So this is magnitude in dB because we take 20 log base 10 of that. But that's not the full story for T because it also has a phase angle. So we need to see how the phase changes. So we know that the magnitude will drop at high frequency. What about the phase angle? How would it change with frequency? This is what we will try to do next. What is the phase angle for a complex number such as this one? T of j omega is K over 1 plus j omega over omega 0. We want an expression for that to be able to construct the phase body plot. So the phase body plot is a plot of the phase angle. And if the phase angle of T, because T is K over 1 plus j omega over omega 0, is the phase angle of K minus the phase angle, not T, the phase angle of K. So let me erase this. Minus the phase angle of 1 plus j omega over omega 0. In our example, K, we calculated it to be 100 volt per volt. And omega 0 is 1 million radians per second, 10 to the 6 radians per second. So the phase angle of a positive real number is 0 degrees minus the phase angle of this complex number, and it's arctan or tangent inverse of omega over omega 0. And therefore phi, if I call the phase angle of T phi, would be minus arctan omega over omega 0. This is the phase angle of T, of the transfer function T of j omega. So let's see, let's look at this function. The arctan would vary with omega, obviously. Let's start first with the value omega equal omega 0. I get minus tangent inverse of 1. And I know this is minus 45 degrees, right? This is well known. If omega goes to 0, that's very, very low frequencies. This is like DC. Then I get minus arctan of 0, and that's 0. Again, we know that. And if omega is very, very large, very, very high frequency, then omega over omega 0 would tend to infinity, and phi would go to minus arctan infinity, which is 90, so minus 90 degrees. So this means that phi is between 0 and minus 90, and at omega equal to omega 0, it goes through minus 45. So between 0 and minus 90, and at omega 0, it crosses at minus 45 degrees. So this is the blue curve that we're seeing here. On the y-axis, I have phi of omega. On the x-axis, I have omega log scale. I can say omega log scale or omega over omega 0 log scale, and the x-axis values would be 0.1, 1, 10, and so on and so forth. Or I can say that this is just omega log scale, and this is omega 0, and this is 10 omega 0, and this is 0.1 omega 0. Either way is fine. So the red is omega, not omega over omega 0. And we see that at omega 0, the blue curve goes through this point at minus 45 degrees. At low frequencies, these are the low frequencies here, as we go towards low frequencies. Notice that in the log scale, I cannot show 0. Because if I go a decade below 0.1, I will go to 0.01. A decade below that would be 0.001. So 10 to the minus 3, 10 to the minus 4, 10 to the minus 5. I will never see a 0. So low frequency is at like our regular minus infinity. This will be very, very low. This will be DC frequency. So this is very, very low frequency here. And you see that the blue curve is approaching the x-axis, so 0 degrees. And then at very high frequencies, here I'll have very high frequencies, very large omega. You see that the blue curve is approaching the minus 90 degrees level. So it really never becomes exactly equal to minus 90 or never exactly equal to 0, except at DC. And it's always between 0 and minus 90, going through the point omega 0 minus 45, as you can see. So this is the blue curve is the exact value of phi, of the phase angle. We can also have some approximations here if you want a quick approximate body plot. And the approximations that we will do here are the following. For all frequencies that are larger than 10 omega 0, I consider that to be high frequency. And I consider the phase angle to be approximately minus 90. So this is the approximate value. For all frequencies starting at 10 omega 0, I would say that this is the approximate phase angle. For all frequencies that are less than 0.1 omega 0, I would say that all of these are low frequencies and the phase angle is approximately 0. So that's a constant phase angle for any frequency below 0.1 omega 0. And between 0.1 omega 0 and 10 omega 0, I will have a drop according to this straight line, which approximates the blue curve and has a slope of minus 45 degrees per decade. So I lose 45 degrees per decade. And it goes through the point omega 0 minus 45 degrees exactly. So there's no error between the approximate red and the exact blue. So the three red lines, they're straight lines, approximate the blue curve. And the approximation is pretty good around omega 0, as opposed to the approximation for magnitude, which had the highest error at omega 0. For phase, the error at omega 0 between the blue and the red is 0. They go through the same point exactly. The maximum error in this case is here at 10 omega 0 and at 0.1 omega 0, and it's 5.7 degrees. But around omega 0, the approximate plot gives me a very, very good approximation. On Moodle, you may find that there are documents that show you how you can construct these approximate plots. And we will return to this topic again soon. So now that we have the body plots for magnitude and for phase, these are in the frequency domain. I want to go back to the time domain and see what is the effect of changing the frequency on the time domain function. So I will apply an input or a source signal, which has the same amplitude and 0 phase. So you see here that I want to take this amplifier that has this transfer function 100 over 1 plus s divided by 10 to the 6. And I want to find the output as a function of time, not VO of s, VO of t, a sine omega t plus phi. When the source signal is 0.1 sine omega t, So phi for the input is 0. The amplitude of the input is 0.1 always. So 0.1 sine, 0.1, 0.1, 0.1. In other words, I am not changing the amplitude nor the phase of the source signal. What I'm changing is the omega, the frequency of the input. So here, for the first case, I have omega equals 100. Here, sine omega t, omega is 100,000. Here, it becomes 1 million. And for the last case, it's 100 million. So this is what I'm changing. I'm changing the frequency, and I want to see what happens to the output as a function of time. Do I get, if the low frequency gain is 100, which is the value of k here, 100, do I always get 100 times Vs, like 100 times 0.1, 10 sine omega t, no matter what? Of course not. We will get the output VO of t would be different at each frequency. So let's analyze. How do we go from the frequency domain back to the time domain? If I have t of s, I can find the time domain value for the output if the input is a sine wave. Dealing with sine waves actually makes going back from the frequency domain to the time domain straightforward. So you take t of s and you go to t of j omega, and you write this as some t at some angle phi. And we have the expressions for t and phi. Right? T would be k over the square root of 1 plus omega over omega 0 squared, and phi is minus tangent inverse of omega over omega 0. All right, so this is t and this is phi, and then the output amplitude, so amplitude of V out would be the amplitude of Vs, which is fixed at 0.1. It's not varying, but if it varies, you take the amplitude of Vs times t, and t is a t of omega. It changes with omega, and the phase angle. So I'll continue here. The phase angle of output would be the phase angle of the input, but the phase angle of the input in this case is 0. All the input is always of the form 0.1 sine omega t, so there's no phi in the Vs of t. So this is the phase angle at Vs, which happens to be 0 plus phi. And therefore, this is equal to the phase angle of t. So the amplitude at the output would be this, and the phase angle of the output would be this. How do I write now the expression for V out of t? If this is t of j omega, so that's my t, and that's my phi. I can write V out of t as 0.1 times 100 over the square root of 1 plus omega over 10 to the 6 squared, sine omega t minus arctan omega over 10 to the 6. So what is this 0.1? This is the amplitude of the input. This here is t sine omega t plus phi, but phi happens to be minus arctan omega over 10 to the 6. So now we see how omega enters in the phase angle and in the amplitude of the output. You see it here, you see it here, and of course it's here, it's the frequency. So now I want to find VO of t at all these frequencies. All these frequencies, 100, 100,000, million, 100 million. So of course I have the expression for V out of t, and then I can just plug in the numbers and I get 4 answers and that's it. But that's not fun. Let's try to guess what the output will be from what we know so far and the value of omega. So starting with the first one, at 100, I compare omega with omega 0. Omega 0 is 10 to the 6. So when I have a frequency which is 100 and my omega 0 is 10 to the 6, this means that omega is much less than omega 0. 100 is much less than 1 million. So I'm close to DC, really. I'm at some very low frequency. And what did we say about very low frequencies that are close to DC? We said that the gain would be the low frequency gain. So my gain, or the absolute value, magnitude of T, would be the low frequency value, 100, right? 100. What about the phase angle? Again, at very low frequencies, we said that the phase angle is approximately 0. So there's no phase angle. So T would be 100 at the phase angle of 0. And that should be a very good approximation at when omega is 100 radians per second. So what will be the output? It will be the amplitude of the input, 0.1, times magnitude of T at very low frequencies, 100. So 0.1 times 100, 10 sine omega T, and omega is 100, plus phi, and the phase angle of the output will be the phase angle of T in this case, because the input has no phase angle. And for very low frequencies, the phase angle of T would be 0. So if I plug in the numbers in the equation here, in the last equation we have, we should get something very, very close to 10 sine omega T. Let's see, if we plug in the numbers, what do we get? Oh, there you go, 10 sine omega T. The approximations, and I did 2 approximations, that T is 100, even though I'm not at DC, but it should be very close to 100, and that the phase angle is 0, even though I'm at 100 radians per second. But if you do the exact computations, you will get maybe 9.9995. So that's 10 sine 100t minus 0.001. So that's nothing. So the approximations that we did would give us a pretty accurate estimate. Let's go to the next frequency, which is 100,000. And here at 100,000, this is this value here. Omega, if it's 100,000, is 0.1 omega 0. 10 to the 5 is 0.1 times 10 to the 6. So at this frequency, omega is 0.1 omega 0. So 0.1 omega 0, it means that we're still at some low frequency, lower than omega 0, 10 times lower, a decade below. So the magnitude of T should still be around the low frequency value, maybe 100, a bit less than 100, but should be around 100. The phase angle at 0.1 omega 0, if I use the approximate phase angle, I should also get a 0. But from the previous slide, let's go back to the previous slide. At 0.1 omega 0, this is a well-known number, like 5.7 degrees. At 0.1 omega 0, the approximate gives me 0, but the exact is minus 5.7. So since I already have this result, I don't need to do the calculation again. I might as well use it. So when omega is 0.1 omega 0, the gain will be approximately 100. That's the magnitude of T. And the phase angle would be approximately 0, but I know that it will be minus 5.7 degrees. So these are my guesses. Let's see what the equation will give me. The equation, the exact numbers are 9.95. I guessed 10, so that's pretty good. 9.95 sine omega T, okay, minus 5.7 degrees. So this is exactly what I guessed for phase. So again, the approximations and the exact kind of match. Let's go to the next frequency, and that's at 10 to the 6. And at 10 to the 6, which is this one, this is exactly omega 0. Omega 0 is 10 to the 6. So now at omega equal to omega 0, what happens? we know what happens. We studied what happens. For the magnitude, omega is called omega 3 dB, and we know the reason why it's called omega 3 dB because the gain drops by 3 dB, and this 3 dB drop in gain comes from, we showed that previously, comes from the fact that the gain actually drops by a factor of 2. So here T would be K over root 2. K over root 2, if you take 20 log of that, you get the minus 3 dB. So this is a well-known result that T at omega 0 for LPSTC is the low frequency value over root 2. So 100 over root 2, or 70.7, because K is 100, 100 over root 2 is 70.7. For phase angle, also I have a well-known result that at omega 0 for LPSTC, the phase angle will be exactly minus 45. Yeah, so T is minus 45. So the output, therefore, will be 0.1 times 70.7, so that's 0.707. And the phase angle of the output will be 0 minus 45, so that's minus 45 degrees. And that's exactly what we get here, 7.07 sine omega t minus 45 degrees. So you see that the output is dropping. It was 10, and then as the frequency increases, 9.95. Now at omega 0, it's 7.07. And you see that it's shifting. The phase is changing from 0 to 5.7 to 45 degrees. Let's look now at the last frequency, which is 10 to the 8. And 10 to the 8 is 100 omega 0. 100 omega 0. What will be the gain at 100 omega 0? What will be the magnitude of T at 100 omega 0? And what will be the angle? Let's look at this number, 100 omega 0. 100 omega 0, I'm now in the range where the gain is dropping. After I cross omega 0, the gain starts to drop. So now at 100 omega 0, what's the situation? Well, at 100 omega 0, how far am I from omega 0? 100 times larger. 100 times larger in decades is 2 decades. It's a multiplication by 10 twice, times 10 times 10. So times 10 times 10, 2 decades. So now I'm 2 decades away. And what do we know about the slope of the line? It's minus 20 dB per decade. Or another way to say this is, if the frequency increases 10 times, the gain drops 10 times. But now the frequency increased from omega 0 to 100 omega 0, 100 times. So times 10 times 10. What does this mean? It means that the gain will drop 10 times 10 times, so 100 times. So if the gain was 100 at low frequency, and now at 100 omega 0, I will be at 100 drop by a factor of 10 for 1 decade, and then by another factor of 10 for the other decade. So 100 over 10 times 10. So that's 100 over 100, and the gain should be around 1. T should be around 1. And this should be a very good approximation. This should be very good approximation. And what is the amplitude of the output at omega equals to 100 omega 0? 1 times 0.1, so 0.1. What about the phase angle of T at 100 omega 0? 100 omega 0 is now high frequency, and the phase angle at these high frequencies would be minus 90 pretty much. So we can also guess that the phase angle of T is minus 90. Again, these are from the results that we have and the approximations that we discussed. So now my estimate for the output is that it should be 0.1 sine omega t minus 90. And if I use the exact expression, I get 0.1 sine omega t minus 89.4. So close enough to 90 degrees. So this is how the output changes. Look at this dramatic drop from 10 to 0.1. Even at omega 0, it was 7, and then 2 decades ahead at 100 million radians per second, it's 0.1. The output is equal to the input in amplitude. If the frequency increases beyond 100 million, the output will be less than the input. Let's move on. And now let's consider not just like a simple circuit with one capacitor. Let's consider an amplifier and see how does an amplifier high frequency response look like. This is actually how the high frequency response of amplifiers we study in this course would look like. So on the y-axis, I have the gain in dB. So that's a magnitude body plot. And on the x-axis, I have f, so frequency, but in hertz, not in radians per second. This can be omega, no problem. And of course, log scale for a body plot. And if you look at the blue curve, this is how the gain would vary with frequency. So there is a range for which the gain is almost constant at low frequency for all this range here. You see that the gain is almost constant. This extends all the way to this point here. And for these small frequencies, the gain is constant at AM. AM is we call it the low frequency gain. And in dB, the gain is 20 log AM. So nothing really happens there. And we just need to know what is this AM, and we know how to do that. We know how to find AM. You do small signal analysis. You ignore the capacitors and things that vary with frequency. You just use the low frequency small signal models. You do small signal analysis, and you get AM, VO over VI or VO over VS. That's AM. Okay, great. But that's not the full story now. Now there's something that's happening at high frequency, and we need to know how is this drop? Where does it start? What is the slope? What is the 3 dB frequency? Do I need to know any details here? Anything that's interesting? So we need to do the study about what's happening at high frequency. Sometimes we need the details, but often we don't want all the details really. We just need the quantity that we call the bandwidth of the amplifier. If you just tell me what's the bandwidth of the amplifier, what's its low frequency gain, that's good enough. So the low frequency gain determines this level, this horizontal level that extends from almost DC, and it's at a level equal to AM or 20 log AM in dB. And this level, we know how to find it. We do low frequency small signal analysis. If I want just the bandwidth of the amplifier, the bandwidth would be the frequency at which the gain, the blue curve, drops 3 dB below the red line. So it's this frequency. We call it FH or F3dB. So FH is a very important quantity. It determines the bandwidth of the amplifier, and often it's the only quantity we are interested in. I don't care about all the other details. Just tell me what is FH. But that's not always true. In other cases, we want to know the details, like how is this dropping? Is this a sharp drop? Is this going like this or like this? Or if I want to know all the details, I will have to learn some techniques to get all these details. If I just need FH, then probably I will use simpler techniques if I just want FH. So now we'll have to learn or come up with some techniques, learn some tools to find the high frequency response, including finding FH when it's the only quantity of interest that we're after. So we will start with the case when I know or I am given the gain, the transfer function. So somehow I am given the gain function, the transfer function for the amplifier. So just like we calculate T of S for that simple circuit that had one capacitor, here I have an amplifier. Someone did this calculation for me. So gave me, VO over VI or VO over VS is this transfer function. It will have this kind of form. So it's a polynomial in S divided by another polynomial in S, and with an AM there. This in general is not always true. There are some transfer functions that don't look like this. But in 311, this is the type of transfer function we will assume. So it's a rational function, polynomial over polynomial. Not just that, it will be of this form. So 1 plus S over omega P1 into 1 plus S over omega P2, 1 plus S over omega Pn. And then there in the numerator, 1 plus S over omega Z1, 1 plus S over omega Z2, to 1 plus S over omega Zn. The number of zeros and the number of poles, before I mentioned zeros and poles, these values of omega P1 and omega P2 and omega Pn are called the poles or the pole frequencies. Omega Z1, omega Z2, omega Zn are called the zeros or zero frequencies. And again, we will consider in 311 that the omega P's are positive numbers, positive real numbers. Again, this is not general. There doesn't apply to any transfer function, but only to the amplifiers we'll study in this course. The omega Zi are called zero frequencies. They can be positive, negative, or infinite. Infinite means that there is like a missing zero. If omega Z2 is infinite, then this will disappear, and this I can remove it. In other words, the number of zeros may be less than the number of poles, and the degree of the polynomial in the numerator may be less than the degree of the polynomial in the denominator. So these are called zeros and poles, and you may have heard, you may know what they are. And for the amplifiers we will study, they're real numbers. The poles are positive. The zeros are positive or negative, or they may not be there. So we consider them to be infinite. What about this AM? If you plug in the value S equal to 0, all the factors there become equal to 1, and A of 0 becomes equal to AM. But S equal to 0 corresponds to J omega equal to 0 in the frequency domain. That's like DC, and AM would therefore be the gain at low frequency. As we approach DC, A of S approaches AM, but we know that A of S should approach the low frequency gain. So AM must be that. AM must be the low frequency gain. So this is the low frequency gain. These are the pole frequencies. And these are the zero frequencies. And it's possible that one or more of the zeros may be infinite. So the factor would be missing. All right, so someone gave me such a transfer function and asked me, can you tell me what is the low frequency gain and the 3 dB frequency and the bandwidth? Well, low frequency gain is very easy. I just look at the value of AM. That's the low frequency gain. What about 3 dB frequency? What about the bandwidth? With all these poles and zeros, what about the bandwidth? What can we do to find the bandwidth? Let's start with a very simple technique called dominant pole approximation. What is this dominant pole approximation? It's a very simple way to very quickly find the bandwidth if the condition is very important here. If there is one of the poles, call it omega p1, if one of them is much less than all the other critical frequencies, yani poles and zeros. If omega p1 is much less than omega p2 to omega pn and to all omega zi, then we call it dominant. And of course, we would ask, what is much less than? Much less than 100 times less? 10 times? No, actually, it's just a factor of 4. If one of the poles is a factor of 4 less than all the other critical frequencies, then we have this dominant pole condition. So 2 octaves down. For example, let's say omega p1 is 20 radians per second, and I have poles at 85 and 150 and 2000 and zeros at 320 and 5000. Omega p1 in this case would be dominant because the next critical frequency would be the pole at 85. And between 20 and 85, there is more than a factor of 4. So this means that I can say that the pole, this one, the smallest, the dominant will be the smallest one, is dominant. The smallest pole is dominant. All right, great. How would this benefit my analysis? If this is the case, here's a very nice approximation. You can approximate A of S by just a low-pass STC consisting of this single pole. So it becomes AM, and then you can remove everything and just keep the factor. So AM over 1 plus S over omega P1. It becomes like a low-pass STC. You can forget about all the other poles and zeros. Everything, you just remove them if a pole is dominant. And this is an amazing result. Why is it amazing? Why all the excitement? Because this is of the form K over 1 plus S over omega 0. So what is omega 0? I'm after omega 0. I'm after the 3 dB frequency. So if I have a dominant pole, it would be the dominant pole would be omega H. Omega P1 is the bandwidth, is the 3 dB frequency. Really very simple technique. Just like sort the numbers. If one is very small compared to the others, then that's it. That's the answer. We don't need to do any calculations. If we're not so lucky, maybe there's a pole which is smaller than the other, but not by a factor of 4, maybe a factor of 3 or 2.5. There is another approximation that we can use, which is this one. So here, all the poles and the zeros would enter in the equation, and you can get an estimate. And we don't need to derive this. It's just an approximation from the transfer function. And this will give you a better approximation when there is no dominant pole. Now, what if there is really like, I'm either asked to get an exact value for FH, or the poles and the zeros are very close to each other. So I can't use these approximations. I can always go back and solve the equation exactly. Is that possible? Actually, yes. I can go back and solve I'll use the definition. What's the definition? At omega h, the magnitude of A is the low frequency value over √2. This is the definition of 3 dB frequency. The magnitude drops by a factor of √2. All right. Can I find the magnitude of A at j omega h? Well, just replace S by j omega h, take the magnitude of this complex number, and you get this, right? So A is AM over √2. So you get AM times like a product of square roots here, divided by a product of square roots here, equal to AM over √2 at the 3 dB value. So AM and AM cancel, and we get this equation, which looks kind of scary, but it's really not that scary, because if you square the two sides and you call omega h squared x, you end up with a polynomial equation, this kind of equation. So polynomial, which may be second degree, third degree, degree 4 or 5, a simple calculator can solve this because it's a polynomial equation. I know omega p1, omega p2, omega pn, omega z1. These are numbers, I know them. So I just need to find the value of x by solving the polynomial, and then omega h would be square root of x. This will be the exact value of the 3 dB frequency omega h. Solve the polynomial equation and then take the square root of the value of x that you get.